discussion for the course Fundamentals of Micro and Nanofabrication. So the instructors of the course are from ISC Bangalore, Professor Shankar Selvaraja and Professor Avasthi. And I am Udiptya, so I am a PMRF scholar, and so I am doing my PhD at IIT Madras. So something more about me is that I completed my Bachelor of Technology in Biotechnology from Delhi Technological University, and I am currently pursuing my direct PhD. So it is MS plus PhD, what we say, and. And so I'm currently pursuing my direct PhD from IIT Madras. So it's Biomedical Engineering Division, and it falls under the Applied Mechanics Department. And I'm currently like working on optical biosensors, and particularly for nucleic acid amplification tests, that like what you must must be aware of with all the COVID and things, the PCR and other tests are also there. So I'm basically working on them, and also parallelly I'm working on nanometer synthesis and its characterization. So you can actively reach me with your doubts outside of the class, like if you have some following up, so you can do so by reaching me at my email ID. So people are requesting. So moving ahead. So this course, week 1, we were basically, so this I would start with a summary, and then maybe like go with some of the problems, and also discuss what is the intricacies and how you have experienced these things. So anybody has any question? So before starting, I would like to reiterate that you are free to ask any questions. Like it's a discussion session, so I will try my best to fulfill your doubts and also discuss, and anybody who knows the thing can also comment. So basically it's kind of a discussion, and I would try, and if I am not able to do so, I would follow it up with the help of my professors or the course instructors, and I would surely provide you the best solution, and try to get you the best solution. So the first week starts with why microfabrication, like why we should do it, and we also discuss the basic workflows and the jargons. So like I wanted to learn that why personally you all have is it? Sure. Just wait. Now it's okay. The audio seems okay now. Shared my screen actually. Sorry. I hope you are able to see my screen. Yeah, now the screen is visible.
No, sir. It's not visible.
It is Not visible? Uh,
Now visible, now visible. Okay.
okay, sure. So that I was discussing about what I am doing and what I read from this slide only. So the week one is why microfabrication that I was telling, and we discussed with the basic workflows and the jargon. So I wanted to ask that what is your motivation to take this course? Like how are you personally benefiting from this course, and how do you relate to this course? Like where you will be applying such the application of those courses. So such some ideas like what are you doing with this? What would be the final goal from what you expect from this course? Can you all type it in the chat? Like some of you must be interested in fabricating something, or some maybe from like what's the thing? You can be just curious also to go on with those ideas. Like microfabrication has a lot of applications. So what application you should be focusing on? You are focusing on. That's like just a thing we can discuss. Okay, you are maybe down the course. You should realize no issues with that. So the second video was why we considered why silicon is the king, and and also discussed some other materials which are also favorable for microfabrication applications like gallium arsenide, and a lot of them. Uh, the third video was upon synthesis methods. So we discussed primarily three methods, I think. The Czochralski method, the float zone, and the Bridgman. And the fourth video was on the workplace, the clean room, and how its intricacies are, and what are the precautions we have to maintain. And the last and the final video was on maintaining the workplace, how to maintain it, and like all the processings that go behind the surface cleaning. So, moving ahead, uh, I would start with something like simple, such that I hope the crowd is interdisciplinary in nature. So, like we know that we are working with semiconductors. So, uh, so the problem one deals with the fundamentals of semiconductors, and it asks that the highest occupied energy level in a band diagram is referred to as. Can you all participate in it and tell like what would be a what could be the like answer to it? Anybody in the chat? You can raise your hand, and such kind of things can also be done. Anything which are comfortable with. So, okay, balance band. Which one? Minimum or maximum? Okay. Uh, okay. So yeah, the highest occupied energy level in a band diagram is the conduction band maximum. So, so if if I tell the highest occupied energy level in a band diagram, which is in the which is in the like absolute zero temperature, what would be that? Like, what do you think that would be? Like with thermal temperature, yeah, conduction band maximum can be reached, but with like absolute zero temperature without any thermal energy there, what could be the highest energy level band diagram that can be referred to as? What do you think, sir? Any ideas? Come on. So, feel free to answer. It's perfectly right to be wrong, and perfectly we can discuss. No issue with it. Any ideas? Okay. So if it's in the ambient temperature, it's mostly the valence band. Oh, sorry, actually I mixed it up. So it should be valence band maximum, which uh, which would be like the occupied energy level at the uh, absolute zero temperature. So, the second question is also pertaining to semiconductors only. So, we have heard a lot about Fermi level and for conductor, insulator, and semiconductor. So, the first question is, what is Fermi level? What do you think so? What is Fermi level? In the lectures, it might have not been like mentioned properly, but like a lot of time it has been mentioned that what about Fermi level. Anybody knows about what is the Fermi level? Anybody can unmute and also tell. They're free to do so. Uh, so, uh, Anybody? Okay, the highest energy level that an electron can occupy. Perfect. For to some extent, at you need to specify something. The highest energy level that an electron can attain at something. So it's the highest the electron can attain at the absolute zero. So if I have a, I hope you can see the structures. Yeah. So let's this conductor, insulator, and semiconductor. It's just that. So let's talk about semiconductors first. Semiconductors. So for semiconductors, if I consider this as energy, so this would be the conduction band, okay, and this is the valency band. So the Fermi level is usually at the, for intrinsic semiconductors, it's usually in the middle of the two bands. So this is what called is the Fermi level. Similarly, for insulator and semiconductor, conductor and insulator, the things happen. But if we consider with semiconductor, this is interesting because we also in the lectures we also delve upon doping that I have mentioned. How does it change with doping in semiconductors? So we have two type of dopings, that is N-type and P-type. So with N-type, we basically have more charge carriers. Okay, so we have more charge carriers. So what do you think? The from the intrinsic part, like this is the intrinsic. It is no intrinsic means no doping. So it has no doping. So what do you think? It should increase, it should be more than the intrinsic Fermi level, or should it be less than the intrinsic Fermi level? What's your take? Towards a perfect answer. Perfect. So it would be like this. Perfect. And for p type, it would be reverse. It would be near the valency band. Perfect answer. So let's go to the next thing. So we have read about the Czochralski method. So it's a small question. So Czochralski method, firstly, to like if I summarize, it has a seed which is lowered in a liquid, so and it is pulled out, and on this the on this when it is pulled out, the single crystal is formed on the like the receding crystals, first on the seed and then on the following following things that have basically immobilized on that seed. So this is the Czochralski method, and it is one of the like most primarily used method for silicon crystal formation. So the thing is, so first, what is the method used for? Like it's a straightforward question. Czochralski method is ideal for what? The first thing is polysilicon to single crystal ingot. So polysilicon is which has a lot of crystals of silicon, to single crystal is single crystal ingot, and polysilicon to prime grade. Prime grade is what we use for mostly for electronic applications. Polysilicon to mechanical grade is that is used for mechanical applications, and third is mechanical grade to polysilicon. So somebody have answered it as polysilicon to single crystal ingot. Any more answers? Okay, so yeah, you are correct. It is polysilicon to single crystal ingot, and so are the B and C options incorrect completely? What do you think so? Or we do find prime grade or mechanical grade? What do you think so? Nice. You can get prime grade, and so these are, so essentially it is a single crystal having a single crystal means it will have a same plane, like it will have a 1 1 1 plane throughout, but it's like quality can differ, but it's essentially a single crystal, which is what is formed with Czochralski method. So following up, for this method, which of the plane is growth of which plane is more difficult? Like growth on which plane is more difficult? That is the question. And there is something that also derives its economy, like how cost effective that method is, and like which is more easier to build. So what do you think so? 100, 111, 111 and 110. Sorry. So what would be a which is you can see that which one is more primarily used, that I think is would be most. Okay. Others can also participate, like. Nice. Okay. So everyone is saying 110. So the easiest growth is done along the 111 direction. That is, we know. and so uh, the like examples, the primarily we will get a 111 plane, uh, like silicon, and this is mostly derived using this is mostly dependent on the surface energy, and which is a property of silicon. So 110 essentially will be very more difficult, and it's more costlier than other methods, the other planes. Nice, you guys are so. So the thing is, in Czochralski methods, why are these single ingots what we get circular, and what is this diameter that they are why like on what factors these diameters depend on in Czochralski method? So in Czochralski method, we see that we usually pull it up from a polysilicon mixture. So, what do you think it is, or what measures it is round in shape or circular in shape? Like the first question that you want to say, why are they circular? The rate of cooling, it can affect the diameter of ingot, but why are they circular? Like, why are they circular? That's the first question that we are focusing on. Nice. Rotatory motion. Yeah, sure. So this is these have a rotatory motion also, like along with it also has a rotatory motion. So this rotatory motion also helps in like maintaining the thermal management also. So like now the thing is what depends, like what is the depend, like how is the diameter of this ingot depends on. First, I think Bandhana has answered the rate of pulling. True. The rate of it is the area is inversely proportional to the rate of pulling. Nice. Another factor. Another factor fast. Correct. The latent heat of, that is the difference delta H, or H in minus H out, whatever, that also has a effect on the, this is directly proportional to the area of the single ingots that we get. True, heat difference. Perfect. So these all methods are like are based on a method on zone refining. So this zone refining means that the impurities have different solubilities in melt and in liquid forms. So in zone refining, so this is the question, that using zone refining method, the final solid is purest, the initial solid is purest, or this in this method the we have equally pure throughout. Okay, initial solid is purest. Anybody has other answer? Anything else? Any answers, and any more options are also possible, because essentially I have made the questions after seeing the video. So any other factors that can also be added is also can also be done. So that's not an issue. You can also give your own comments or your own arguments. You can actively discuss on this. Yeah, Meenakshi.
So initial solid is purest.
Okay.
because in zone defining we are taking an
Mm-hmm.
initial ingot
Mm-hmm.
for this process, and that crystal is taken to be the purest form,
Okay.
and then it attracts the purest molecules and atoms towards it to develop that rod.
Okay. But you look okay. That thing is good. But can you follow it up? Like why the other part is impure? Why does it happen?
Why does it happen?
Yeah. You are correct
Okay,
in for the first sense that why the initial solid is purest.
initial
Uh,
sol. So like what I think is that it then goes back into chemistry, and the well,
sure, sure, no issue. You tried your you the
actually I'm not getting those words
uh-huh.
because this inclination, which is indicated by an arrow, na, so that uh, I'm not getting the word for that. It
Mm-hmm.
is similar to other atoms which are of the pure form. That is why they attract the other pure atoms also.
Okay, okay, okay. So yeah, the pure thing you have done, you have explained properly, and I think is agreeable to a lot and like everyone. So yeah, what Meenakshi is saying that yeah, like so essentially like like if I try, it is like we have a pot and it has a lot of polysilicon and it can be impure also, so it impurities and purities everything is there. So essentially when you put our seed, so the silicon will the like it has different solubilities in melts and liquid. Okay, so the melt so it will like a very when it solidifies, very less impurities will be on the solid part. Okay, so it would be the purest. But as we are pulling it out, the volume of this solution will decrease. Okay, and the impurities concentration will increase. Okay, in comparison to the silicon concentrations. So what happens is that though there is yeah, so there is more chance of the impurities getting deposited on the silicon ingot that is found. Yeah, uh, everyone getting it? Am I able to explain it? Sure, sure. Okay, very nice. Meenakshi, you have any thoughts? Okay, 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 nice. So we'll get to the next thing. So after we have read, we also see that this Czochralski method is not ideal for gallium arsenide. And so, what would be an ideal method? First thing to ask is why gallium arsenide has been like we why like where we find gallium arsenide applications in in day-to-day life. Do you see anything where we find gallium arsenide applications, and what would be its ideal use depending on its properties, semiconductor properties? Anybody? You all know anything about direct band gap and indirect band gap? Yeah, food detector. Yes. So you all know about direct band gap and indirect band gap. So gallium arsenide is a direct band gap or a indirect band gap semiconductor? What do you think? Direct. Okay. So essentially, it means that this is the conduction band, this is the valence band. They are in same like same planes. So what happens is that energy is not like in some materials it is shifted. So this is indirect, this is direct. So these are very good for this energy like light emitting devices or photodetectors. So these are very good for such applications. So in this, there some energy is lost using some other transportations like phonon transportations or other transportations are also there. So that reduces the energy of the things. So why Czochralski method is not ideal for gallium arsenide single crystal formation? Anybody? Okay. So it's gallium arsenide. When we melt it, so arsenic has a very low melting point. And yeah, right. Arsenic evaporates. Yeah, so it starts evaporating. Okay, and these give rise to this such structures that you would be finding like all like the ingots forming like this. Okay, but they have come up with some solutions like using boron, which can help in capping this this arsenic release. But this boron capping has also some issues. What do you think so? So essentially, we have gallium arsenide, and we know that its arsenic has a low melting point, and it evaporates when we do the Czochralski thing. But we have a solution also that boron can be used to cap it and trap it in the solution, trap it in the system. But this boron thing is also has an like disadvantage. Can anybody tell it? Like, mention it. What is the challenge with boron capping? Yeah, true. And it happens in the interface of boron oxide. So this boron oxide leads to this loss of heat. So which leads to the situation. Nice. Nice answer. So during the course, you have learned a lot about the wafers, silicon wafers, and this wafer flats signify certain information about the silicon wafer. Okay, and so the angle between this primary and secondary, if it's present, of a single silicon wafer, what does it indicate? So we have options: crystal orientation, dopant type, doping concentration, wafer production technique. Okay, guys, what do you think? So mostly these questions are like I have derived using the current assignments and like also like looking at the videos and mostly the past questions. So they are very relevant to the questions what you would be getting in the current assignments. Okay, somebody has answered crystal orientation. Okay. Anybody has any other answers? Any more answers or anything to the list? Anything adding to the list? Essentially, it can have multiple answers also. So you can specify that. Doping concentration. Okay. Any others want to try? It's completely fine to get wrong. Anybody else? Different type. Okay. Only dopant type? Tell in combinations, like what combinations you think? Doping concentration, okay. Any more, any more? Actually, I haven't found the perfect combination yet. People have been partially right, but yeah, the perfect concentration is what I was looking for. Anybody would like to answer? Okay, cool. So, this crystal orientation is what we discuss about the different planes, like what planes it would be 1 1 1 1 1 0 1 1 1 0 0. Dopant type is N type, P type. Okay, doping concentration is how much it is doped, and wafer production technique, like the other methods what we discussed, Czochralski, Brodso, different kind of methods. So it usually depends on the like here this is the wafer flats, and we can see like we can derive two information from this. One is this one, that is the crystal plane. Okay, 100 100 111 111. So this tells about the crystal planes, what the up, like the up portion is, and the angle, like this is the angle that we were talking about. So this the angle between the primary and the secondary flight, the primary being the essentially being the larger one and the secondary being the smaller one. So, and another information is what we get is the type of doping. So we essentially get two informations. One is the crystal orientation, another thing is the dopant type. Okay. So doping concentration is something we can't see from this thing. And wafer production technique also. So that's such type of things I believe is available at the spec sheet of the wafers. But essentially, with the only the wafer in front of you, you can only derive two information. That is the crystal plane and the type of doping. Okay. So with in the wafer processing things, there is one important method, that is chemical, and we polish, like polishing to the mirror finish. So, like, can but anybody quickly tell why polishing is important? Why important?
Polishing, there are small pits and the surface is not smooth.
Mm-hmm.
Microscopic pits are there,
Mm-hmm.
so polishing is required to make the surface more smoother.
Okay. What will happen if it's more not smooth? And why it is mirror smooth? Why does it say like this? Why what will happen if it's not properly smooth?
If it's not properly smooth, then there would be vacancies, or because this fabrication is also mm, at like atomic level also, no? So
Mm-hmm.
that we'll have to come at its crystal structure,
Mm-hmm.
and
Yeah, yeah.
then there would be vacancies, and maybe some interstitial vacancies would be there, which would be filled by with this.
True, true, true. So essentially, what from the fabrication, like the device point of view, like if I have something that is not like irregular, so we deposit usually some structures in it. We usually make structures. So essentially, if I have made this structure, which is some this length in this length is same, so I would have thought this would be would have been spread like this, but for this gap, what you were saying as a pit, my device would be like this, and it would be like this. So this irregularity will have this repeatability problem. We are essentially making a lot thousands, and we're scaling it up these chips in on single wafer. So such kind of repeatability, we want repeatability. So with this gaps, we won't be able to get the desirable structures may not be formed. So in chemical mechanical polishing, the wafer replace the wafer, like, if you can recall, where do you place the wafer? Before that, why like mechanical polishing? Okay, because, okay, can anyone tell why it is chemical and mechanical polishing? What's the chemical and mechanical entities they have? Mechanical entities, during the polishing, what is the mechanical part and what is the chemical part that we are using? Can anyone tell to get the mirror finish?
In the cleaning process, we use Piranha solution or RCS solution. That is the chemical part. Okay.
Okay, but this wafer, during this is we are talking about the wafer preparation stage. This RC clean and like the other Piranha treatment is where you would start with making the structures. So this is like very before, like very like a very like where we are preparing the wafer. Uh, Piranha thing is when you will do, you have a wafer that you have bought, and how to do it, like that's the stage. But this is like the wafer production cleaning that we are referring. Anybody has any idea what could be the chemical and mechanical parts here? So for the new ones who have joined, we are discussing about chemical mechanical polishing. And in the chemical mechanical polishing, we are discussing that what are the chemical and mechanical parts here. So anybody would like to answer? Or anybody who would want to make some guess, that is also accepted. Okay. So in chemical, if you recall, we are using some kind of oxides like alumina, Al2O3. So these oxides act as abrasives. So they are usually used for this polishing, and mechanical is the same, the rotor that usually is involved in it. So this is the action of chemical plus mechanical. So can you tell where the wafer is loaded on in the chemical mechanical polishing? Anybody want to try? Conditioning head. Okay. Any other answers? One more answer I will take. Then we can discuss the answer, the solution specifically. Polishing head. Okay. So essentially, it is the polishing pad, that this yellow thing you see. So we usually have this polishing pad, and we place our silicon wafer on it, and we have this motor which have a rotatory motion, and it usually like have this heavy weight, and like grinds through the surface, as that we get a. So you can see two motors are there. So this is the rotatory part, and we usually drop some abrasives here. So that's, I think, that is what gets to the chemical thing. So the problem 10, we are discussing about the clean room. So clean room, as you understood from the week 1 videos, that it is the workplace, and it is one of the important parts of microfabrication, nanofabrication techniques. So what this is very surface question, that what is the advantage of performing microfabrication process in a clean room and clean room environment? We know that clean rooms can go very costly, and maintaining them is very costly. Can anybody tell the different levels of, like, how many levels we have in a clean room? That, I think, can tell why it is very costly. Does anyone recall how many levels are there in a clean room facility? In a like top-notch clean room facility, essentially, yes. I'm not saying of the classes are different, but essentially, if a top class, what does a clean room look like? That I am telling about, like what are the different partitions that it has, and I think that would help us appreciate why is it so much costly. Five levels. Okay. So first level is where air flows through. Okay. The second is the clean room. Okay. Yeah. Correct me if forgot something or something. And this is the sub clean room, and this is the I think sub fab they tell it, and this is the utility level. Essentially, these are the levels. Yeah. So clean room has a perforated flooring, so air can pass up, and it has some output. Here we have some special filters. Anybody can tell about the filters? What are they called? These filters. These are special filters. Huh? I couldn't hear it actually. Sorry. Sorry, can you repeat? Sure, perfect. HEPA filters. So we filter it through it. So essentially, what would be the advantage of performing microfibrillation in a clean room environment? Anybody answer? B. Downtime of flow of filtered air reduces the risk of dust particles contamination on the wafers. Okay. Any other answers? Okay. Essentially, this is the correct one, and this perforated that I explained is what allows this flow of filtered air through this system. So the problem 11 is what that we were discussing for wafer cleaning for for using it in fabrication. So these are the steps. These are the different steps we perform. So what do you think? So what would be the order of the wafer cleaning? You must have in the last lecture you must have undergone the different cleaning procedures, the RCA cleaning, the Piranha cleaning, and all those. I haven't mentioned the names. I have only mentioned the constituents, and we can go ahead with the what are they, and while discussing we can figure out what are they. So the first process. Anybody? The first process. Which one you think would be the first process of wafer cleaning for using it for fabrication? Anybody? Yes, you would like to answer?
First of all, go for the AS202 and AS2SO4 was. RCA cleaning, before we go through the pre-cleaning. And after that we go through a RCA cleaning. RCA cleaning,
So
there
this
a
is what you are telling, H2O2 plus H2SO4.
Yeah.
What do you do in this picture usually?
This is pre-cleaning.
Pre-cleaning? Okay. And
And
what do we usually tell this mixture as a special name?
yeah, this is called a piranha.
Pirana, perfect, Pirana. Okay. And or they tell it SPM,
Yes.
sulfuric peroxide mixture.
Or mix. SPM,
Okay.
sulfuric acid mix.
Okay. So the next.
Next step is the RCA cleaning. In RCA cleaning, there is a three step.
Okay.
SC1 and SC2,
Mhm.
and after that DHF,
Which one is
dihydroxyl.
SC1? Which one you do you identify as the SC1?
SC1 is NH4OH plus H2O2S. Okay.
Okay. So can you tell which one H2O2 plus H2SO4 why pre-cleaning is important? Like what purpose it is serving to?
Because there is lot of oxygen or organic matter or organic particle is in there, and
Mhm.
for that purpose there is a reaction between H2O2 and H2SO4. There is possibility of a radical creation or oxidizing agent that will oxidize that. There is
True, true.
okay.
So yeah, the most important thing is organic contaminants. So we remove organic contaminants with this, and plus uh, okay. The
The,
next thing is yeah. Yeah. Tell
ne-
anything you
is,
would like to add?
the next thing is SCA1, Radio Corporation of America RCA1. Okay.
Mm-hmm. So you were
And
telling
then
NH4 plus OH. So this is the
OH.
first
That
one. First one. So this is the second one. Okay.
and
So
the second
NH4.
one particularly because of particulate organic matter involved. Okay.
Okay. So like what kind of things how do these particulate matters get washed off? This is essentially alkaline wash, yeah.
Yeah, yes, yeah.
Okay.
And
So how do?
this is H2O definitely a oxidizing agent.
Okay. Alkaline wash. So like anybody has any idea like how does it? Like he told it perfectly. It is they use for particulate matter wash, but can anybody tell how is it like working? Okay, essentially this changes the charge on the particulate matter, or which say scientifically zeta potential, yeah,
Yeah,
on the thing, and this like gets off from the surface, and also this ammonia also forms some complexes with this some of the metals. So some of the metals can also form soluble salts, and they can wash off from the surface. Yeah, cool, perfect. Third one. The third one. Anybody would like to try? If anybody recalls it.
I don't think there is a HCF2 solution is there, but we
Hmm?
can go for the hydrogen fluoride also. The last step of in
No,
the
this so after alkaline wash, we usually go with the acidic wash.
water acidic.
Uh, okay, so acidic wash. So essentially, some of the with alkaline wash, we can't remove the alkali metals. Alkali metals means the sodium, potassium group. So we have to such materials we have to remove through the sorry, I think it is HCl plus H2O2. Sorry for the sorry. HCl plus H2O2 solution we have to go with. This is done perfect like usually for the alkali metals. So these alkali metals would like form a salt with HCl like NaCl, KCl. Such soluble salts can be derived out from the silicon wafer, and then the next step
HF wash.
HF wash. HF wash is for
But another particulate matter which is not removed by the conduct of oxygen, because hydrogen fluoride is much more efficient.
Essentially, because we are using hydrogen peroxide in each step, it is usually for the SiO2 that would be formed on the surface to etch it.
Silicon oxide.
Yeah, HF, I think you remember it. And the penultimate of the penultimate one, second last is the second last would be
Water wash.
perfect water wash. So this is one of the important parts. Such that because if we forget water wash, it is like we are adding so much chemicals, so it is basically chemical washing, all the washing of the chemical. Okay, washing chemical. And the final step would be the blow dry, and we usually using nitrogen or spin. So perfect. Yeah. So we have crossed the 1 hour mark, but I have a last and final question that we know that device reliability is an important when fabricating device for commercial use, where long time requirement is required. However, reliability issues cannot always be determined immediately after fabrication. So which of the following characterizations can be done at the time of fabrication? So you have the options. Just go on which you think would be a perfect thing, which could be detected shortly after the fabrication of a device. Which characterization essentially the question is which characterization can be done perfectly like shortly after the fabrication of a device. And these checks are very important in quality check. These big firms have like strict QC measures, quality check measures, and they are very strict with maintaining the quality of their devices. So such type of things are usually done in these industries, and they usually get this QCs, and any device that doesn't perform in the QC, they usually reject it. So you all have any answers? Anybody? We'll be after this question we'll be closing the session, and you could anybody have, if any doubts, they can stay back or ask. B or D? B or D? Okay. Anybody? So the next week also we would be having this session, so I request everyone to complete their week 2 videos, and then we can fruitfully discuss whatever issues we have. So essentially this answer is particle contamination. So this is what we can see through the primarily through microscopies, this particle contamination, and the other things like the corrosion due to this will take a lot of time, like corrosion will happen a lot, environmental humidity, this strain induced, so we will need various strain giving methods, and we would like use it different with time we would see it, and this also like fatigue due to cycle loading of a device. So all these will take time is involved in it. So I think with particle contamination you can just take out your device whatever is there, and you can see what are the particles which are contaminating your pattern. So here we close the session. Anybody has any doubts or any discussion or any comments, like how would you go with the sessions? As this is the first session, I would like to improve, and I am also new to this, so I would be happy to get any feedback. Thank you very much. Anybody has any queries, any comments, any feedbacks? Feel free to do so. Yeah. The session would be uploaded in the YouTube. I think in 1 hour or so. I think I would be uploading the videos. Yeah. So yeah, I think the NPTEL team would also give you the recordings, or otherwise the next session I will also give you the link, or maybe if I can give you the link now only officially. So anybody has any questions, any comments that you would like to add, that you would like, and any feedbacks also that that will help me go on with the future sessions. So essentially we will meet next. So I will also give the link of the channel, such that you can, whoever has missed the sessions can essentially see. So okay, I think I got the video link. So you all can see this, see the videos here. I will upload the videos within 1 hour, I think, and also I would also be giving out the PPTs, I think through the NPTEL portal, so you all also can access to it, get access to it. And if any doubts, you can write to me, to my mail ID, and I would be happy to solve them. Thank you, guys. Yeah, hopefully the next meeting would be more beneficial. I'll be staying here for some time. If anybody has any issues, they can discuss. Otherwise, people they are free to leave. Thank you all.